Thanks for joining me. We're about to go through and do some practice problems. Now, you know we've heavily invested in this. In particular, if you look somewhere down here, you'll discover there's a pause button. That's an amazing feature of this video. You see, what you can do is once you see a problem, pause. Think about how to do it. Better yet, do the whole problem. And then, once you're ready, unpause. And even if you can only do part of it, do as much as you can. The more you can do by yourself, the better you'll get. All right, let's begin.
Starfleet Intelligence has recently learned of a new Borg vessel that can change its shape, nicknamed the B-1000. Now, the B-1000 has some limitations, namely, it's always the shape of a box. Okay, so it's a box, all right, great. The volume is fixed, always 3,000 cubic meters. Currently, we can only see 2 of the 3 sides. The length is 20 meters, and it's decreasing at a rate of 2 meters per minute. The width is 15 meters, and it's increasing at a rate of 1 meters per minute. The question, what is the depth, and how fast is it changing? All right, so we have our formula. In fact, it gives us here volume, length, width, depth. Okay, so let's go ahead and write that down. So volume is length times width times depth. But remember, volume is fixed at 3,000. It's not changing. The length, the width, and the depth, that can change, but not the volume. So we say, okay, so that says 3,000 is equal to length, width, depth. Okay, and so there's our relationship. That's what ties these 3 quantities together. What else do we have? Well, we have some information. So let's write down what we know. We're given the following. We're told length is 20, so L equals 20, and it's decreasing at a rate of 2 meters per second. So it's a rate. Rate is a fancy word for derivative. So that says dl dt. Decreasing means going down, so minus 2. Width, w, is 15. And it's increasing, so that's a positive, at 1 meters per minute. So that's 1. And all right, so that's what we're given. Now, we can use this to answer some questions pretty quickly. Namely, what is the depth? Well, we know 2 out of the 3, so we just plug it in. And all right, so we find the depth, find d. We can say 3,000 is equal to 20 times 15 times our depth d. Well, 20 times 15 is 300, and that says then that 3,000 is equals 300 times d, so d must be 10. Okay, and in fact, we can even say more. It doesn't ask for units, but they often do. So depth equals 10 meters. All right, great. Now, what about the derivative? The rate of change, right? So for that, we need to take a derivative. Okay, so let's say we want to find, I'll call it d prime. All right, and so where this is L prime, and this is W prime. So what do we have? Well, taking the derivative, we have that 0 is equal to product rule. Product rule with 3 terms. Now the nice thing about product rule is it follows a very simple pattern. Everybody gets a turn. So we say, all right, let's start with L. L, you're up. It's your turn. Me? Yes, you. So L takes the derivative. W and D stays as they are. Now it's W's turn. Wow, W, woohoo! So what's going to happen? L stays as is, W takes the derivative, and then D stays as is. Finally, it's D's turn. Say, all right, so what happens here? It's LW, and then derivative of D. So we now have our relationship for our rates. So we plug in. We say, okay, so that says 0 is equal to L prime is negative 2, W 15, D 10, plus L, which is 20, W prime, which is 1, and D, which is 10, plus L, which is 20, times W, which is 15, times D prime, which we don't know, but we're going to know it really soon. All right, so we are almost there. So let's multiply this out. 10 times 15 is 150, minus 2 is minus 300. So we get 0 is minus 300. And here we have 20 times 1 times 10 is 200. So plus 200. And then here we have 20 times 15 is another 300. Well, minus 300 plus 200 makes minus 100. Move it across. That makes a positive 100 equals 300 d prime, or the change in d, the derivative of d, with respect to time, is 1/3. And now, what are the units? Meters per minute. And there we go. All right, so the missing dimension, the depth, is 10 meters. The rate at which it's changing, 1/3 meters per minute. Great. Wow. All right. Find the linearization L of x of the function secant x at x equals pi over 6. Okay, so we're going to have to do linearization, but you know, linearization is just essentially a fancy way of saying tangent line. So there's kind of a clue. Linearization starts with line. And so linearization is the best line. And what's the best line in calculus? The tangent line, of course. All right, so we're after that. And we see we have a trig function. We're at an angle of pi over 6. So for reference, I'm just going to write down the angles. What's going on at pi over 6? Cosine of pi over 6 is equal to root 3 over 2. Sine of pi over 6, that's equal to 1 over 2. Now, what if I want other interesting angles, such as our function? Say I want secant. All right. How do you get secant? You flip over the cosine. And all right, so secant of pi over 6, that's 2 over root 3. And if you're somebody who really does not like to have a root 3 downstairs, well, you can multiply this by root 3 over root 3 and get 2/3 root 3. Okay, and now, of course, other things you can look at, tangent. All right, what happens with tangent pi over 6? Well, tangent's sine over cosine. So you end up with a root 3 over 2 divided by 1 over 2. The 2's cancel, essentially. You can multiply top and bottom by, I got that backward. Sine over cosine. There we go, I can do math. That's 1 over root 3. Again, multiply top and bottom by root 3 over root 3 if you like. So that's 1/3 root 3. Okay, so that's reference, just in case. All right, so what do we need? Well, we need to know what's happening for the secant function at pi over 6 and what's happening for the derivative of the secant function at pi over 6. So we have our function f of x equals secant of x. We have our derivative, which is secant x tangent x. And we plug in. So f of pi over 6, that's equal to secant of pi over 6. And we've already figured out that that's 2/3 root 3. F prime of pi over 6, well, that's secant of pi over 6 times tangent of pi over 6. Well, secant of pi over 6, that's 2/3 root 3. And then tangent of pi over 6, that's 1/3 root 3. And so if we multiply, well, root 3 and root 3 multiply to get 3. There's cancel with one of the 3's downstairs. So we end up with 2/3. All right, wonderful. So what's our linearization? Well, that says secant of x is approximately our function f of pi 6 plus our derivative f prime of pi 6 times x minus pi over 6, which in our case makes this 2/3 root 3 plus 2/3 x minus pi over 6. And that's our linearization. It's the tangent line. Nice! Woohoo! Find the linearization of f of t, which is 4t over t squared plus 6 at t equals 2, and use this to estimate f of 2.05. So the idea is linearization is an approximation to the function, because the tangent line is an approximation. In some sense, it's the best approximation as a line near the point of tangency. So we have our tangent line at 2, and 2.05 is near 2. True story, true story. Okay, so we proceed like we were finding a tangent line, because we are finding a tangent line. So we have our f of t, 4t over t squared plus 6. And now I'm going to take the derivative, well, quotient rule. So we take low, bottom, times root of the top, 4, minus the top, 4t, times root of the bottom, 2t, all over the bottom term squared. Now, we can clean up the top a little bit. So we have 4t squared minus 8t squared. And we also have 4 times 6. So 4 times 6 is 24. 4t squared minus 8t squared will give us a grand total of minus 4t squared, all over t squared plus 6 quantity squared. All right. Now, with the function and the derivative, we're going to plug in 2. So, say, all right, what is f of 2? Well, 4 times 2 is 8. 2 squared is 4 plus 6 is 10. So 8 over 10, or I can write that as 4 over 5. How about f prime of 2? Well, 24 minus 4 times 2 squared. That's 24 minus 16, which is 8. Downstairs, 2 squared is again 4 plus 6 is 10. Squared, don't forget to square it. So it's 8 over 10 squared. Well, okay, that's 8 over 100. And if we wanted to, we could write that, well, 100 is divisible by 4. And so we can write that as 2 over 25. All right, good. Now, our linearization, what will that look like? Well, now that we have our function and our derivative at the point we're interested in, we put it together. We say, okay, so f of t, and we'll just make a note here to the side, this is near 2. F of t is approximately f of 2 plus f prime of 2 times t minus 2. Well, so that's approximately 4 over 5 plus 2 over 25 times t minus 2. All right, so that's the linearization. Now that is part of our answer. So this is our linearization, because it says find the linearization. So here we go. Let's make sure we celebrate our successes. And now it says, hey, use it. So how do we use it? Well, the linearization is an approximation to the function. So we plug in. So f of 2.05. So that's going to be approximately 4 over 5 plus 2 over 25, 2.05 subtract 2. And let's actually see if we can't clean it up a little bit. I think we have a shot. So 2.05 subtract 2 is 0.05. Okay, so that's 4/5 plus 2 over 25 times 0.05. And now 0.05, that's this piece here is like the same as 5 over 100, or if you like 1 over 20. So if we look at it for a moment here, what can we say? Well, that's approximately 4 over 5 plus 2 over 25 times 1 over 20 is the same as 2 over 500. Okay. Well, now normally we're going to reduce down. This time I'm going to actually go up a little bit. So up saying, I'm going to get our denominator bigger. 5 and 500 both go into 1,000. So imagine the first term, that would be multiplied by 200 over 200. So that's 800 over 1,000. And then here you have to multiply by 2. So plus 4 over 1,000. And you say, all right, so that's like 804 over 1,000, or 0.804. And that's our estimate, which means it hasn't changed much. However, the function 4t over t squared plus 6 will not be changing much at that point, and it doesn't get incredibly large. In fact, it stays bounded. So this is not such an unusual answer that we have here. So all right, there we go, 0.804. Nice. Woohoo! Use linearization to give an estimate for the fourth root of 600. All right. Well, let's think about how can we approach this. So we need to have a function, and we need to have a place on that function that we're trying to do linearization. And so we look at this particular thing and we say, okay, we have the fourth root of 600. So what this looks like is it looks like we've plugged 600 into the fourth root part, right? So it's the fourth root of 600. Do you see how you had that like pause, like the fourth root of 600? So it's like, oh, 600 is your input, fourth root is what you're doing to it. So the fourth root is your function. So now it's like, oh, okay. So we're really thinking what we're trying to do is approximate f of 600, where f of x is the fourth root, x to 1/4. Okay, so this is telling us that's what we're asked to do. Identifying the function. Okay, so that's actually a non-trivial and important step. The next step. Okay, so we know which function we want to do our linearization with. Where will that linearization occur? Well, we have to think about this. It's not an immediate like, aha, it must be here or it must be there. It's like, think about it for a moment. So what we want is we want to have something close-ish to 600, but also something which is really convenient in terms of the function. So a quantity that when we plug it into the fourth root, we get a nice number out. So another way to think about it is sort of like, oh, the kind of numbers that work really well when we're taking fourth root are things which are fourth powers. So we can start thinking about, well, what do the fourth powers look like? Well, we'll do whole numbers. So 1 to the 4th, that's 1. 2 to the 4th, 2, 4, 8, 16. Okay, not even close to 600. 3 to the 4th, let's see, 3 times 3 is 9. Then you can think of 9 times 9, that's 81. Okay, so all right. How about 4 to the 4th? Oh, now we're getting interesting. Think about 4 squared. That's 16. And 16 squared is 256. Because, everybody loves powers of 2. Who doesn't remember walking around when they were teenagers thinking about, let me do powers of 2, 2, 4, 8, All right. Still not close to 600. How about 5? 5 times 5 is 25. 25 times 25 is 625. So 5 to the 4th is 625. That's looking promising. Okay, what about 7 to the 4th? Now, 7 squared is 49. 49 squared is big. So 49, so 7 to the 4th, I think that's somewhere around 2,301. Roughly speaking, that's in the right ballpark. So looking at this, you say, okay, which 4th power is fairly close to 600, relatively speaking? And it's like, oh, this 625, that's not too bad. So now we have an idea. So we're going to let's update our plan. So our updated plan. We're making notes here. We're going to find the linearization of the function f of x equals x to 1/4 at x equals 625. So we need to know what function we're doing the linearization of, and we have to figure out where we're doing the linearization. Because if I ask, okay, here's this function, there's infinitely many linearizations I can attach to that function. We're trying to find the one that's close to where we're at. So it feels in some sense it's like we haven't started the problem yet, but we've actually done the hard part, which is we figured out what we need to be using. So now that we've done the hard part, let's enjoy the rest of it. All right, so now for the rest of the story. So we have our function, x to the 1/4. We take our derivative, f prime of x. That'll be 1/4 x to the minus 3/4. So plug in 625. And what do we get? Well, we get 625 to the 1/4. But we know that because we said, hey, 5 to the 4th is 625. So 625 to the 1/4 is 5. Okay, how about f prime of 625? Well, we can think of this as 1 over, there's a 4 there. Now, the x to the minus, that's why we moved it downstairs. X to the 3/4, we can think of that as first starting by taking to the 1/4 power and then cubed. So this is 1/4 to the cubed is 3/4. But we take this to the 1/4 power first because it's easier to shrink and then get bigger versus get huge and then try to get smaller. So if you have this shrinking and expanding, shrink first and then expand. 625 to the 1/4, we've already talked about, is 5. So this is 1 over 4 times 5 cubed. Well, 5 times 5 is 25. Times another 5 is 125. So we get this is 1 over, 4 times 125. And if you like, that's 1 over 500. All right. Good. We're making progress here. Now, with this in place, we're ready to do what? Well, we're ready to do our approximation. So we say, okay, so near x equals 625, f of x is approximately the function at 625 plus f prime of 625 times x minus 625. So that's approximately our 5 plus 1 over 500 times x minus 625. And our last stretch, our final push, and then we're done, is we say, well, we are after the fourth root of 600, which is f of 600, and 600 is, relatively speaking, close to 625. At least when it comes to convenient numbers, it's relatively close. So we'll accept it as a reasonable approximation. So that's going to be approximately 5 plus 1 over 500 times 600 subtract 625. Well, if you take 600 subtract 625, you get negative 25. So this is minus 25 over 500. Okay, well, 25 goes into 500. And so this is the same as 4. And in particular, 500, if you multiplied it by 20, well, if you take 25 times 20, you get 500. And so this is 4 minus 1 over 20. Or if you like, that's 3.95. Because 1 over 20 is 0.05. So our estimate for the fourth root of 600 is 3.95. Is it right? No, it's an estimate, right? That's the whole point. Estimate says, I'm not telling you exactly what it is, but I'm going to give you a really good ballpark for what it is. And you know what? As I say this out loud, I can see that I messed up something. 5, not 4. I don't know why I put that, but okay. 4.95. That's even better because I copied stuff down correctly this time. Yeah, you know, small mistakes. They're the most annoying ones. So be careful. But 4.95, it's not exactly the fourth root of 600, but it's close. It's very close. And if you were on a desert island with coconuts and you were wondering to yourself, what is the fourth root of 600? This is a great answer. It's a wonderful time doing math with coconuts in paradise. Is it because of the coconuts or is it because of the math? It's probably both. All right. Find all the critical points of the function f of x is e to the 3x over 3x squared minus 1. All right, so where do we begin? Well, what are the critical points? They are places where we have boundary, but there's no boundary. There's nothing listed here. Our derivative is undefined, or the derivative is 0. So it sounds like we're going to be taking a derivative. You are correct. We're going to take a derivative. All right, so to take this derivative, we're going to use the quotient rule. So f prime of x is, we're going to take the bottom, 3x squared minus 1, low, times the root of the top. That's going to give us 3e to the 3x, minus the top, e to the 3x, times the root of the bottom, which will be 6x, all over the bottom term squared. All right. Well, let's work on that top for just a moment. We can factor an e to the 3x out. Actually, we could probably do a little bit better. Let's factor 3e to the 3x, right? Because there's a factor of 3 there. And I'm seeing that e to the 3x is common to both terms. So 3e to the 3x. And if we factor that out, we have a 3x squared from here, a minus 2x, and then a minus 1. All of that divide by 3x squared minus 1 squared. Now, what are we looking for? Well, is the derivative ever undefined? Is the derivative ever zero? Let's start with the zeros. So for the zeros, you look upstairs. This is where we look for zeros. And when we talk about undefined, usually we look downstairs. So this is tend to look for undefined. We're going to have a conversation, but let's hold back on that till we get there. So we'll start with the upstairs. So we say, okay, if f prime of x equals 0, well, that says the numerator equals 0, so that gives us 3e to the 3x times 3x squared minus 2x minus 1 equals 0. 3 can't be 0, okay, so that's not a problem. And e to the 3x can never be 0. It's a very optimistic function. It's always positive. It's a function that always looks on the bright side of life. Okay, so anyways, the moral is the exponential function, always positive. Okay, great. So we can ignore these pieces. Then we have this polynomial left. 3x squared minus 2x minus 1. Does it factor? Can we try? It seems like it might. Let's see. If it were to factor, it would have to be, since it's 3x squared, it has to be a 3x and an x, and because that's a 1, it has to be a 1 and a 1. Now let's see, what do we need? They have to have different sign, and we have to end up with -2. So I'd want the minus here and the plus here. Does that work? 3x squared, yeah. Minus 3x plus x is minus 2x minus... Yeah, that worked! Ho, 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 ho. Oh, that's not... They care about us. They like us. They want us to get the right answers, right? Of course they do. Now, that tells us what? Well, this tells us x equals minus 1/3 or x equals 1. Because we just now, the reason we factor is we say, hey, if you have a lot of stuff multiplying and you get 0, something had to be 0. And so it turns our big problem into little tiny problems. So we say, okay, great. So these are places where we have critical points, where the derivative is 0. All right, good. Now that finishes the top. What about the bottom? Well, if I look at the bottom, I say, okay, if it's undefined, the only real issue I have with anything is a division by 0 problem. There's no square roots of negatives. There's nothing. Well, undefined, that would be if 3x squared minus 1 is 0. However, here's the thing. This will not be a critical point because notice if 3x squared minus 1 equals 0, we do a very big dramatic motion here. Did you see that big flowing arc? What can you say about 3x squared minus 1 being 0? This is not part of our domain. So it's not part of our original function. And so as such, because it's not part of our original function, it can't be a critical point. Critical points have to be places where our function is defined. Now there are examples where the function does exist, but the derivative doesn't exist. A very simple example is something like the absolute value of x. Right? It does exist at 0, but the derivative doesn't exist at 0. However, in our case, the only place where our derivative is undefined is our function's already undefined, so there's no critical point coming from the derivative being undefined. So what's our final answer? Our final answer is these 2 points. So we say, okay, our critical points are at x equals -1/3 and x equals 1. And we're done. That's it. Ha! Wah! Huzzah! Huzzah! List all the critical points. All of them. What? All right, of this function t of theta, which is tangent squared theta plus 4 secant theta, for theta in this interval. Now, what it's really saying here is, you might look at this and say, like, what's going on here? But essentially it's saying, look over one period. So, if you think of it as the unit circle, we're going all the way around a unit circle. And why in this format? Well, because if you look at tangent of pi halves or secant of pi halves, it's undefined at pi halves and 3 pi halves. So we're just saying, don't even think about those points. Our function's not even defined there. So it's like, okay. So we've removed the places where our function is not defined. So now we're really after, what can we say about our critical points at our sort of derivative being an issue? All right, well, here we go. It's going to be fun. Critical points. All right. Now, I would do the following. We're going to say, look at t prime. What's the derivative of tangent squared? Well, take the chain rule. 2 comes down. We have tangent, and to the 1 power, and the derivative of tangent is secant squared. And now we're going to add 4. What's the derivative of secant? Secant tangent. All right. Good. And, well, these have some terms in common. They both have a tangent, they both have a secant, and they both have a factor of 2. Let's pull all that in front. All right, so we've got 2 tangent theta secant theta times, all right, what do we have here? Let's be careful here. We have a secant theta and a plus 2. Okay, good, good. Now, what do we care about? Well, is this ever undefined? Well, yeah, if tangent is undefined or secant is undefined, but we've already taken those points out. So, boom, those are gone. Okay, well, if those are gone, what else do we have to worry about? Well, zeros. Okay, so we have a couple of possibilities. When does tangent of theta equal 0? When does secant of theta equal 0? And when does secant theta plus 2 equal 0? One of these three is going to be very quick. Can you tell me which one? This one is not possible. Secant can never be 0. It's a number that's either bigger than 1 or below -1. So in other words, it's never close to 0. And another way of saying this is 1 over cosine equals 0. Well, that's not going to work because that says that 1 equals 0. Okay, forget it. Hopeless, hopeless. All right, but now tangent equals 0. Well, when does that happen? Well, there's a couple ways to think about this. If you say, well, think of this as sine over cosine, that's the same as saying I want the top to be 0. So that's like sine theta equals 0. And you're like, oh, well, I can now channel my unit circle and be like, I am thinking of my unit circle. And the sine is the y value. So this is y equals 0. So these are the points we want on the unit circle. What angles do that? Well, the answer is 0 and pi. Okay, so that says we've got to add 0 and pi to our list. So 0 and pi. Now, we're only doing 1 full revolution, but it would be 0, pi, 2 pi, 3 pi, so forth and so on. All right, so from tangent equals 0, we get theta is multiples of pi. All right, so we've started our list. Well, all right, but let's keep it going. This other part, secant of theta plus 2 equals 0. Well, that's the same as saying secant of theta is negative 2. And if you're not comfortable with secant, you can say, oh, that's like 1 over cosine. So 1 over cosine theta equals negative 2, or cosine theta is negative a half. All right, so we can come back here, our exact same picture actually, and say, oh, this would be where x equals negative a half, and cosines are x values. So sines are y values, cosines are x values. So there are two angles that we need here. And we say, okay, now what angles would they be? Well, kind of need to know your unit circle a little bit. It helps. It helps. But here's one way to think of it. You could say, okay, what's going on? Well, what's going on here is if you were to draw this triangle, that would be an equilateral triangle. So what angles make an equilateral triangle? 60 degrees, or if you like, pi over 3. So we say, oh, okay, so it's pi over 3 off of the negative y-axis. So what angles are being involved? So this angle would be like pi, pull back pi over 3, which is 2 pi over 3. And then this angle is pi plus another pi over 3. So we end up with 2 pi over 3 and 4 pi over 3. All right? And those are the only two angles between 0 and 2 pi which have secant of theta equals negative 2. So that says we add those two to our list. 2 pi over 3 and 4 pi over 3. All right? And now we said, look, we've had these three pieces. We figured out what happens to tangent. Nothing can happen here. We figured out what happens with the secant, negative 2. And we're done. That's it. We made it. Oh, phew, thank goodness. Oh, all right. Well, good. Good. Now, you might be wondering a couple of things. Like, I made a bold claim that said, hey, this right here is an equilateral triangle. Why is that true? Well, what's true is you can say, hey, this is exactly cutting in half so that this angle matches with that angle. This side has length 1, so this side has to have length 1. And this side has length 1 because it's a unit circle. And all that together tells you, yeah, equilateral triangle. All right, well, that's the reasoning. And, okay, good. Not a little tricky if you don't remember your trick, but if you do, nothing too surprising. Take the derivatives, factor out what's in common, break it up into pieces, and figure out what happens with each part. We can do this. I believe in us. We're great. We're wonderful. List all critical points for the function g of t, 2t minus 7 e to the 2t minus 8t times t minus 6. All right. Well, where do we need? We need to take a derivative. Now, before I'm going to take this derivative, I'm going to distribute this 8t through. I don't know why they didn't do that before, but I'm going to do it now because I can. And yeah, let's actually distribute everything through. So let's go ahead. 2t e to the 2t, subtract 7 e to the 2t, minus 8t squared, minus makes a plus, 8 times 6 is 48t. Okay, so that's g of t, just written it in a little bit more convenient way. So take our derivative, product rule, go to the first, 2 times the second plus the first, 2t, times the root of the second. Root of e to the 2t, 2e to the 2t, chain rule. Minus 7 times root of e to the 2t, 2e to the 2t. Minus 16t and plus 48. Okay, well, let's see. Hopefully, things are going to simplify. And if not, it's going to be an interesting problem. Of course it's going to be an interesting problem. They don't give us boring problems. All right, so 4t e to the 2t. So let's start with that, 4t e to the 2t. Now here we have 2 minus 14. So that makes a minus 12 e to the 2t. And on the other hand, we have minus 16t, and okay, and plus 48. Now, there we go. There's our derivative. Now, never undefined. All these are perfectly fine pieces. No border, no boundary. Great, beautiful. So where's our only place to look? We're looking for zeros. Because it's not polynomial. Yeah. So what do we do? Well, it seems, looking at this, we don't want to panic, because panicking doesn't help. I think it's okay to sort of take a step back and say, did we do everything all right? And so far, everything seems okay. Our derivative definitely would have e to the 2t's. It definitely would have terms without e to the 2t's. But perhaps we can say, well, let's sort of think of it as two parts for right now. We have one part which involves e to the 2t, and then we have a second part which doesn't involve e to the 2t. So maybe let's try to think of what's going on with those terms. And let's see if something nice happens. So what I mean is, let's factor out the pieces. So we're essentially, I would call this like we're chunking together, right? We have this part, we have that part. So here, we'll factor out an e to the 2t, and let's go ahead and factor out a 4. Okay, so that's 4 e to the 2t, and if we factor that out, we get a t and a minus 3. Okay, how about here? Not a lot, but we can pull out 16, that's common. Let's go ahead and pull out minus 16, because I always like to put a positive coefficient on my highest power. So that's t, and if we take 48 and factor out negative 16, that would be minus 3? What? What? Oh my, is it Christmas? Did Christmas come early this year? Oh my, oh wow. Oh, this is cool. See how they both have t minus 3's? Okay, this is great. Let's factor out. So again, so here we factored out the common, and here we factor out in common. Now we're like, oh, common. And also we can factor out a 4. All right, so let's do that. So we have 4 times t minus 3 times e to the 2t, and here, minus 4. This is great. This is the kind of stuff we love, because our goal is we're going to be taking our determinant and setting it to 0. That's how we find critical points. And when we're finding critical points, the ideal scenario is to have a bunch of stuff multiplying. Because a bunch of stuff multiplying equaling 0 says, oh, your problem really is breaking up into little tiny subproblems. And you say, let's look at each part. Well, the 4, that can't be 0. Okay, so nothing going on there. The t minus 3, that could be 0. That would happen at t equals 3. Or we could say, oh, the e to the 2t minus 4 equals 0. Now that could happen. That's if e to the 2t equals 4, right? Move it across. Now, try to get the t out. So currently it's inside that exponential. So we want to say, well, what undoes an exponential? Logarithms. So we take the log of both sides. 2t equals log 4. And then we say, okay, so t is a half log 4. And if you want, you can actually say, oh, you know, you can take this and move it inside. And so that's log of 4 to the 1/2. So this is the equivalent to saying log 2. And now we said, okay, so our derivative is 0, which is our only place that we have a chance for a critical point at one of two places. So our final answer for our critical points, we have 2 of them, and they are at t equals 3 and at t equals log of 2. And that's it. We're done. We did it. Yay, us. Yay, us. Wow. Oh, this is so cool. Did you see that? That was really cool. That was really cool. Water runs into a conical tank at a rate of 15 pi cubic feet per minute. The tank stands point down. It has a height of 12 feet and a base radius of 4 feet. So I want to get a picture going here. So point down, it's a cone. So just saying our point, the tip of the cone is down. And the base radius is this radius up here. So this is 4 feet. And okay, we'll go ahead and put units there. And it has a height, so it's this part right here, of 12 feet. All right, so there's our cone. Good. Now, water is running into the cone, and so you can think of it as though water's being poured into the cone. All right, so do I have a good, let me grab a blue here. I found a blue. So here is our water coming in. And so we say, okay, there's water coming in at 15 pi feet cubed per minute. All right. And, okay, great. I needed a darker blue. So 15 pi feet cubed. There we go. Okay, all right. So that's our water coming in. So if water's coming in, the water level's going to be going up. All right, so what do we have? The question, how fast is the radius of the surface of the water in the tank changing when the water is 3 feet deep? So we have down here, there's some water, but right now it's changing. Then there's some height to it, h. There's some radius to it, r. And we want to find the question. So what's our goal? We're asked to find is how fast is the radius of the surface of the water changing. So we're trying to find dr dt when h equals 3. All right. Well, this will be interesting. We got to start thinking about how to put this all together. Well, some good news here. We do have a formula. For a cone, volume is 1/3 pi r squared h. So we'll write that down, and we're going to start thinking about what's going on. So, where to begin? What a lovely problem. Now, if we look up at this, it seems very three-dimensional, but I want to say actually we can slice it. So I want to think about slicing, what that would look like. So if we slice, then we can draw our picture up here. Our cone becomes a triangle. And in particular, this length up here is 4. This length is 12. And now, where our water is, This is our water. And, whoops, gotta go grab my blue again. Gotta blue it. There we go. There's our water. And we have, okay, this is our height h. And I'm not calling it h equals 3 because it's a thing that's varying. When something is varying, I want to give it a variable name because I don't want to think of it as being 3. I want to think of it as it's currently 3, but it's changing. So I want to be able to be flexible. And then here we have r. Now, what is true? Well, what's true is that we are in a situation of what's called a similar triangle, which is to say this triangle down here where the water is matches the triangle of the tank. Now, when you have similar triangles, you also have similar ratios. So that tells us that r, this r here, is to h as 4 is to 12. Now, because we're after understanding radius, I'm going to solve for h because I want to get rid of h. I want to put everything in terms of radius. So I'm going to move this across so I get r. And by the way, 4 over 12 is the same as 1 over 3. R is 1/3 h. Or, another way to say this, h equals 3r. Okay, so now let's update our formula for volume. Volume is 1/3 pi r squared times 3r. The 3's cancel, so we get that volume is pi r cubed. So if I know the radius of the water, then I know the volume. And in a way, kind of vice versa. So now we're almost there. We're almost there. We've got a formula that connects volume to radius. Now, you might say, why were we doing all of that? And I should have took more time at the start. So let me talk about why we're doing all of that. Do you see this part right here? Water is coming in at a rate of 15 pi cubic feet per minute. This is a change in volume. So they gave us a rate for volume. What are we looking for? We're talking about how fast is the radius changing. So that is a change in radius, dr dt. So while we have a rate for volume, we want a rate for radius. So if we want to do that, what we want to do is find something that can glue these two ideas together. So that's what's going on here, is we're gluing these ideas together. And so I said, okay, I want a formula that connects volume to radius. And so we started with our formula for the volume for a cone, and then said, I want to get rid of the h. And because the radius and the height are connected, if I know the height, I should know the radius and vice versa, gets us down to one formula. One formula to rule them all. All right. Now, we're almost there. Take your derivative. Now, what derivative are we talking about? Derivative with respect to time. We're thinking of everything as being dependent on time. So we have that dv dt is equal to 3 pi r squared dr dt. And we know dv dt. That's 15 pi. We know 3 pi is 3 pi. And now we're almost there if we knew what r was. But we can figure it out, right? We're told h equals 3. R is 1/3 h. So r is 1/3 times 3, which is 1. So that's 1 squared. So what's our great aha? Well, 15 pi divided by 3 pi gives us a grand total of dr dt is 5. So our final answer, right over here, is dr dt is equal to 5. Now we can actually talk about measurements. Our measurements of distances have all been in feet, so it's feet. Our measurement of time has been in minutes, so 5 feet per minute. And there we go. And you might say, that seems pretty fast. Well, but it's also 15 pi. That's a lot of water being pumped into this tank. It's not the largest tank in the world, so it's not taking very long to fill up. So it's filling up relatively quickly, especially when we're near the bottom. The closer you are to the bottom, the more quickly you're filling up. So yeah, it's a reasonable answer. So there we go. Good, good. So I will say, when you do encounter cone problems, almost always slice it and say, oh, similar triangles. It happens. I can't think of a time that I haven't done that. So be ready to use your similar triangles on the cone problem. A particle moves along the curve implicitly defined by 3xy cubed plus yx cubed equals 2x squared plus 2y. When the particle passes through the point 1, 1, its x-coordinate is changing 1/3 units per second. How fast is the y-coordinate changing at this instant? All right, so we have our 3xy cubed plus yx cubed equals 2x squared plus 2y. Okay, now this is our relationship between x and y. We're also told x-coordinate is changing 1/3 units per second. That says, oh, we know dx dt is equal to 1/3. And we know x and y. So here, x equals 1, y equals 1. They might say, well, how do you know this is x and this is y and not vice versa? It doesn't matter. They're both the 1. All right, great. So what do? We take a derivative. Now, be careful here. This is not implicit differentiation, right? There's sort of two schools of thought, and they're very similar. So implicit differentiation would be if you were looking at this and like, oh, this would be y is a function of x. Whereas, what are we doing? Well, we're saying, oh, we're thinking of x as a function of t and y as a function of t. So they have different goals. If I was trying to say how does y change with respect to x, that's implicit differentiation. But if I'm saying how do both x and y change with respect to t, that's related rates. We are in related rates because see how it says dx dt. It's not x coordinate is changing 1/3 unit per change in y coordinate. It's per second. So it's per time. Okay, so make sure you know what setting you're in. Because I could have asked a question about implicit differentiation which uses that exact same formula. So you just want to pay attention. Use the right tool at the right time. So what's the right tool? Well, we want to take the derivative with respect to time. You know, we cue off of what's down here. What's downstairs tells us the kind of derivative we want. So we say, okay, derivative with respect to time. And be patient. We are going to do a product rule. So derivative of the first, 3 dx dt times the second, y cubed, plus the first times the derivative of the second, which is 3y squared dy dt. Yes? So where's this 3y squared dy dt coming from? Chain rule. Derivative of y cubed, 3 comes down, y to the 3 minus 1 times derivative of the inside. All right, and then similar, right, for the rest. Derivative of y, dy dt, and then leave the second term alone. Plus, leave the first term alone, derivative of the second term, 3x squared dx dt. Now, the other side equals derivative with respect to t. Not with respect to x, not with respect to y, with respect to t. That's going to be 4x dx dt. Right? The 2 comes down, x to the 1 times the derivative of x, plus 2 dy dt. And now we plug in the 3 things we know. We know x, we know y, we know dx dt. So we say, okay, we get 3 times a third times 1 plus 3 times 1 times 3 times 1 times something we don't know plus something we don't know times 1 plus 1 times 3 times dx dt, which is a third. All right, that's good news for us. Good insofar as we get lots of 3's canceling, is equal to 4 times 1 times dx dt 1/3. That's not going to cancel, but that's okay. Plus 2 dy dt. Now, the only thing we don't know is dy dt. So we're just going to clean up here. Here we have 3 times 3, which is 9, plus 1. So if we just put those together, that would give us 10 dy dt. Here, the 3 and the third cancel. The 3 and the third cancel here. So we get 2 plus 10 dy dt equals, here we get 4/3. And then we have plus 2. Well, okay, so we're going to move things around. 10 minus 2 gives us 8 dy dt equals 4/3 minus 2, which is 4/3 minus 6/3. And that's negative 2/3. Finally, because we're very close, divide by 8. So we say, dy dt is 1/8 times negative 2/3. Well, we can do a little bit of work here, and we end up with minus 1 over 12. So minus 1/12. And that's our answer. There we go. So our y-coordinate is changing at a rate of negative 1/12. And could we say any more? We could say units per second. In this case, it doesn't ask us for units. And I'm already at the edge of the page, and I feel like it won't add anything. So I'll just stop right there. Okay, there we go. Ooh, nice. We're getting close to the end. Find the absolute min and absolute max of the function h of s is 2s cubed plus 9s squared, and our interval is from -4 to +1. All right. So notice we have a nice function. It's continuous because it's polynomial. Polynomials are some of the nicest functions you'll ever work with. We also have an interval which is closed, which means we include our endpoints, and it's bounded. So we know there is an absolute min and an absolute max for this function on this interval. So how do we do it? We're going to channel our inner Santa, which means what? We're making a list of critical points. Yes, we're going to find out which ones are the best. Okay, what do I mean by this? Well, so we start forming a list of where the max and min might occur in terms of the inputs. So those are called our critical points, and they're going to come in potentially 3 flavors. Boundary points, and I always put boundary points first because it makes me feel good to see progress. And also so I don't forget about them, because occasionally it might be a long problem and you might forget to throw the boundary points in, and they may have been where they happened. So you have to worry about that. Now the other 2 places involve the derivative. One is where the derivative is 0, the other where the derivative is undefined. But polynomials are beautiful. So we only have where is the derivative 0 left to consider. So we start by looking at that. We say, okay, look at h prime of s. That would be the derivative of 2s cubed, 6s squared. Derivative of 9s squared, 18s. All right, well, that was pretty simple. Now, what do? Set this equal to 0. Well, it looks like there's a factor of s in common. And that's because there's a factor of s in common. So let's go ahead and pull that out. 6 times s, and here, s plus 3. Now, so the factoring was pretty easy on this one. If it's a slightly slightly more difficult, slightly harder, you can say, look, divide out by any common coefficients, and then it probably would factor. Because remember, our calc teachers, oh, they love us. Oh, they really do. They're going to give us problems that we can solve. Great, great problems that are very solvable. All right, so now we say, okay, when can this be 0? Well, the 6, no, that can't be 0. S can be 0 at s equals 0. And s plus 3 can be 0 at s equals minus 3. Now, these are potential points to add to our list. The only thing you have to be careful of, do they fall in the interval? Well, 0 is between -4 and 1, so 0 makes the list. -3 is also between -4 and 1, so -3 again makes the list. So there are 4 critical points, and we've made our list. And now we've done, in some sense, the hard part. So after you've made a list, you can check it twice. Yep, feeling good about it. We want to plug each one of these back into our function. All right, so we want to find h of each one of these values. Now, 2 of these will be pretty quick to evaluate, and then the other 2 will take a second. H of 0, 0 is a friend. 0 plus 0 is 0. How about 1? H of 1, well, that'd be 2 plus 9. 11. Okay, that's looking pretty good. So, -3 and -4. Yeah, let's start with -3. So we'll do some scratch work over here. So 2 times -3 cubed plus 9 times -3 squared. Now, -3 times -3 is 9, times the -3 again will get us to -27. So this is 2 times -27. And here we have plus 9, and -3 squared is 9 again. Or that's -54 plus 81. And if you take -54 plus 81, you get 27. So, h of -3, 27. All right. All right. Great. Now, what about -4? So 2 times -4 cubed, right, because we're plugging it in, plus 9 times -4 squared. Okay, well, -4 times -4 is 16, times another -4 would get us all the way up to -64. -4 squared, 16. 9 times 16. Well, 2 times -64, that's -128. 9 times 16 is, say it all together, 144. Good, good. We said it all together. Nice. And if you take 144 and you subtract 128, the result is 16. Okay. So 144 subtract 128 is 16. Okay, so that goes here. Now, what are we looking for? After we made our list, then we plug them in. These numbers here, one of these numbers is the largest, and one is the smallest. It's possible you get repeats, no problem. We don't care about repeats. We're just saying, what's the largest value? What's the smallest value? Well, the largest value is the 27. So that tells us that our absolute max is 27. And we can put a parenthetical comment, occurs at x equals -3. We don't need it, but sometimes it'll ask, where did it occur? And so if they ask us, we're ready to provide that. Our absolute min, okay, so we look, and aha, our smallest value is here, is 0, and this occurs, not surprisingly, at x equals 0. And there we go. We found our absolute max and our absolute min. Did we do it? Absolutely. Yes, we did. Yes, we did. All right, great. Well, another week, another set of problems, and I hope you're doing well. Keep at it. Keep at it. This is hard because we're trying to change the way that we think, but we're going to think even better. We're going to understand how to solve problems better. And once we do that, things are going to be so much more fun. Math does become fun. It becomes play. So keep at it. I believe in you. Thank you for doing all the hard work. I hope all the best. And I'll see you again.